Dobro jutro. Hello, everyone. Good morning. Thank you very much for waking up this early, for just coming to listen to me ramble for 30 minutes. I hope that what I say will be at least mildly of interest, and hopefully I'll inspire you to think about some of the things that recently I've been thinking about in the domain of artificial intelligence that I'm quite excited about. So, my name is Petar Veličković. I'm a staff research scientist at DeepMind and an affiliated lecturer at the University of Cambridge in the UK. And I'll be talking to you about some of the truly amazing things that happen when artificial intelligence systems are paired up with top human domain experts. And this is something I've had the pleasure of partaking in research on over the past couple of years, so I hope that I'll be able to speak from direct experience. So, we are at an AI conference right now, so clearly I don't have to talk too much to this audience to motivate some of the amazing things that AI can already do and the ways in which it's already affecting our lives. Just some that you might be aware of. AI can currently fold proteins at a superhuman level. They're capable of playing video games better than most top human players. They are also pervasive in some places where you would not necessarily expect them. For example, AI is now supporting a state-of-the-art system for estimating wind movements so that we can more accurately price wind energy and therefore make it a more competitive renewable energy source on the market, because usually it's really hard to predict just how much wind you're going to get in a particular day. And also, there are many ways in which it's plugged into the products we use. So if you have even just a smartphone, an AI system interacts with you many, many times during the day. One of the most recent examples that came from my company, for example, is this one over here. AI is currently helping decide what are the next videos to recommend you to watch on YouTube after you have seen a couple of videos, right? And also, it's used to optimize the very procedural aspects of supporting companies like Google that serve you these products. For example, our company, DeepMind, has deployed these AI systems inside Google's data centers to control the cooling of the cooling systems, so that they are not too switched on or too switched off at any particular point, so that they're just right. And just by doing this, DeepMind has managed to cut down Google's electricity bill by about 40%, which for a company like Google is a pretty huge deal. Some people say that we have even paid off our initial investment by doing something like this. So there's a lot of really fantastic things that AI can do. But before we can dive into this more, I know a lot of the people here are already AI-minded and have probably already worked in some AI-related endeavors. But just for the people in the audience that might be more tech-adjacent and might not completely understand where we're coming from, and just to make sure that we're all on the same page about the many different aspects of interacting with AI systems, I'm going to just start by doing a very relaxed introduction into what AI systems are today. I apologize for those who might perceive this as a little bit slow. It's going to pick up in pace very quickly. So, when we say artificial intelligence, what we mean is, roughly speaking, the science of building intelligent things. But what we mean today when we say artificial intelligence is usually this red circle in here, the circle of deep learning, which are techniques that are able to adapt directly from observing raw data. I'll explain what this is in a second. But the key concept that I'd like you to take away if you're not familiar with this stuff, and I found it quite transformative even after spending many years in AI research as a thesis, is that if you want to program a computer to be smart, it's really, really hard. And it's significantly harder than programming it to learn to be smart by itself. Let me illustrate this with an example. Just another nice exercise for you in the morning to get your brain stimulated. Here's a nice little picture. There's no trick question. Can you tell me what you see in this picture? A cat, yes, or mačka, as you would say in Croatian, I hope. And but the thing is, you saw this. You saw the picture, and your brain immediately jumped to saying, yes, that is a cat. So what I'd like you to think about now is why. What was it that you saw in this picture that got your brain to say, yeah, this is a cat, immediately? Why is this important? Because if we wanted to program a computer to look at a cat picture like this, a bunch of pixel intensities, and to say, yeah, that is a cat, we'd need to write down some rules to look at these parts of the image and to figure out what it is. So if you think about it for a little bit, there's probably a few things that come to mind, like the cat has very characteristic ears, has very characteristic eyes, and so on and so forth. You might say, all of these things, and it might be plausible to write a program that hunts for ears, hunts for eyes, and so on, and then says it's a cat. Well, I take all of those rules that you just came up with, and I raise you these two counter cats. I bet you didn't think about any of these guys when you came up with your rules, right? You cannot see any eyes. not really. You cannot see very clearly defined ears, and this cat here is blending with its environment very nicely, so it would really confuse some of those computer systems as to what's the cat and what's the sink, right? Yet, I bet you, once again, you saw these two counter cats, and immediately your brain jumped to saying, I'm looking at a cat, right? And I'm not even beginning to talk about the variety in sizes, the variety in colors, shapes, all of those things that make up a cat, right? For all of us, this is very obvious. For any system that you program by hand, super tricky, right? So why am I telling you all of this? Is because if we cannot come up with a concrete set of rules, then how does your brain know to look at a cat like this and say, that's a cat, even though you've never seen this particular cat before in your life, I presume? Well, one way in which I like to think about it, the way most people in deep learning like to think about it, is that the way it works is that as humans, we have seen many cats in our lifetimes. We walk around the streets, we see them going around us, and maybe at a few points in our life, probably when we were little, there was some supervisor behind us, like a parent or something like that, telling us, yeah, trenutno gledaš u mačku, you're currently looking at a cat, right? And then our brain kind of learned to make the connection between these interesting shapes of the body of the cat and the concepts of what a cat actually is. And that's exactly what we want to capture in deep learning systems. So we want to train this machine learning system, this neural network, to look at the pixels of the cat and then gradually get better and better at predicting that there's a cat outputs. How it's going to do that? Well, this box here, this neural network box, and I'm never going to be peeking into this box during this talk, by the way, for a good reason. But basically, this box looks at the pixels, and initially it has some parameters that make it decide what the thing on the image is. And initially it's going to be really terrible at predicting this. Like you might show it a picture like this, and it will say it's an elephant or something like that. But then gradually we tell the network how wrong it is, and it gradually adapts the parameters so that it gets better and better at predicting cats to the point where sometimes it's more powerful than, say, a state-of-the-art human-based system, right? So that's great, but now the question is, if you want to, say, use these networks not just as a cute cat classifier, but also as something that can have real industrial and scientific value, very often you might be interested in what has this neural network actually learned to do. So what is the rule that maps these images to cats? This is where we're at a bit of a loss as an entire field. I would say there's not many, if any, artificial intelligence experts right now that will tell you what has this model actually learned to do. So for all intents and purposes, you can imagine it as a bit of a black box, and honestly, you wouldn't really be wrong if you do that. I would say the top peaks of our understanding of these systems haven't really matured beyond just this is some black box of parameters that turns out to be really, really good. Yeah? But even though it's a black box, there are still some interesting, very rudimentary ways in which we can interact with these systems that can lead us actually already to scientific and industrial benefits. The first one, because these models are not just classifiers, they're what we call probabilistic classifiers. They will tell us for this particular input not just what it is, but how confident the network is in that prediction. So we can usually ask the network not just what's on the image, but how confident are you in it. So it might say, I think this is a cat with about 97% confidence. This, as we will see, can be a remarkably powerful way to interrogate the model, even though it gives you just one bit of information. A second thing you might want to ask, because this neural network is a bit of a differentiable system, so you can kind of imagine asking it which parts of the input in a gradient sense excite you the most. So which parts of this image helped you arrive at this conclusion the most? And you might expect a sensible system like that to highlight, as we said, the eyes and the ears. Now, I must stress, this is a technique that, as I like to say, is still in its diapers, so it's very easy to get it wrong. It's very easy to be adversarial to get it to see something completely unrelated in the image, rather than the parts of the cat that matter. But I will stress that even in this rudimentary stage where we are right now, you can use this question, which patterns in the input influenced you to make this decision, to actually do some meaningful science. We'll talk about this as well during the talk today. Okay, so hopefully that was a bit of an introduction to make sure we're all on the same page about these models and what we can do to them. Now I will take a step back to show you some interesting synergistic examples of these systems with human domain experts. I'll tell you a little bit about my core area of research. I work on graph representation learning. So I build machine learning models that are capable of looking at this irregularly structured graph data, which is just a general interconnected structure of nodes and edges, and making real-world decisions based on them. Why am I a big proponent of graphs? If you've seen any talk from me, I'll always say graphs are everywhere. We should all be doing machine learning on graphs. It's because graphs are really the true data structure of life. starting from the lowest levels, like the molecule, which is a very natural graph of atoms connected by chemical bonds, all the way to the connectome structure in the human brain, where you have neurons talking to each other in very interesting patterns. And not just natural patterns, also human-invented synthetic patterns. Road networks, or say this transportation network, the London tube map, is very nicely reasoned about as a graph of different intersection tube stops connected by metro lines. And social networks, like this old snapshot of the Facebook friendship graph, also very nicely reasoned about with a graph structure. So graphs are truly everywhere, in nature as well as in synthetic inputs. And therefore, it would probably be a good idea if we want to build a generally intelligent system, that system is able to reason about these structures. And now, there's obviously something that brought me on this stage talking to you all about this. I must have some claim to fame in this area that got me here. And in my case, the first claim to fame is Google Maps. So I hope many of you use Google Maps in your day-to-day life, or Waze, or something similar like this. One of the very important products that Google Maps offers you is this nifty little travel time estimate here. So rather than just giving you a route from A to B, it will also tell you how long does it take to travel from A to B, okay? Now, this is a super important thing, not only if you're a user of Google Maps, but also if you're an enterprise relying on what Google Maps gives you. So say companies like Uber, ride-sharing companies, and food delivery companies, many of them leverage the Google Maps API to tell to their customers when will their cab arrive, when will their food arrive, and so on and so forth. So this is a system that truly impacts billions of people on a day-to-day basis, directly or indirectly. And obviously, as I told you in the previous slide, you now are all well aware that transportation networks are best reasoned about as graphs. And as part of a research team at DeepMind, I have exploited the fact that the road network can be seen as a graph. And we deployed one of these graph representation learning techniques inside Google Maps to predict the travel time. And this is now a system that's been deployed everywhere in the world. But back when we released it in a handful of cities. And here you can see, but just by how much relative percentage improvement, it improved the previous Google production system, which did not use the graph structure meaningfully. So in some cities like Sydney, we cut down on the proportion of badly predicted travel times by over 40%. So it's a pretty massive thing. It was also covered quite a bit by the press, like this VentureBeat article over here. But fundamentally, this graph neural network is now deployed everywhere. So even in Zagreb or other parts of Croatia, if you ask Google Maps for the best way to travel from A to B, the travel time estimate you're going to get is coming from the system that we have co-developed at DeepMind in collaboration with Google Maps. This is the first time I receive an applause after this point, but thank you very much. Thank you very much. Yeah, that is true. That is true. Okay, so why did I tell you about graphs? Because if this got you excited enough and you're an AI engineer or researcher and you want to get into it, if someone gets into this field for the first time, you're very likely going to start by working with these guys over here. Molecules are like the bread and butter of any graph representation learner's day-to-day job because it's the easiest graph data to obtain in huge quantities. We just know molecules are very naturally represented as graph structures of atoms and chemical bonds, right? So what might be interesting tasks that we can predict over the molecules? Well, these kinds of small molecules, this guy over here is paracetamol, by the way, very important small molecule. You might want to predict, could we use them as a drug, right? One very popular class of drugs, for example, is an antibiotic, a drug that eliminates bacteria, yeah? So you might imagine training a neural network, which now looks at a graph, so I've added conveniently a graph term in here, takes this molecular structure as input and predicts, does this molecule inhibit a certain bacteria, like Escherichia coli or something like that, right? And this is something you can build a large data set of. We know about many molecules. We know for many molecules whether or not they're antibiotics. So let's train a system like this, right? And what's really cool about this system is that once you've trained it, you can apply it to any molecule you want, not necessarily just molecules from your training set, and it will give you some probability, as we said, as to whether or not it will inhibit bacteria, right? And you sometimes might come at a situation where it takes a molecule like this, which might be quite unusual. Nobody studied it as an antibiotic, but they studied it for some other drug possible treatments, so therefore it's already passed some clinical trials, so it's useful if you want to, say, ship it on the market or something. And it might say there's like a 99% confidence that this guy inhibits bacteria. Now, I am not a chemist, so I cannot say this with certainty. I hope there's some chemists in the audience that can verify this. But basically, nobody ever expected this guy over here to be an antibiotic. It has a very unusual structure for what a human would expect an antibiotic to look like. Yet, this machine learning system trained on a bunch of antibiotics says it's highly confident, right? So, maybe the machine learning system is wrong. Often machine learning systems get it really wrong in a very terrible ways. However, it just might happen that it got it right. So let's take, say, the top 100 molecules from our data set with the highest confidence and just, send them to chemists. Let's see if chemists can find something interesting there. And it turns out that within those 100 molecules, this guy that I showed you here, which is called halicin, by the way, happened to be a super, super potent antibiotic, all right? And the fact that, as I told you, nobody would have expected this structure to be an antibiotic meant that it had a very different mechanism of action from the antibiotics humans are expected to find, and therefore it was strong even against the bacteria that have developed resistance to antibiotics, because as you know, we're putting antibiotics into our systems over the past decades on and on and on again, and the bacteria have evolved to counter that, right? Well, they did not evolve enough to counter this because we never used it as an antibiotic before. And this was naturally a really big discovery. It was published in one of the top-tier journals, the journal Cell, and very quickly the news spread like wildfire. Nature reshared it, Financial Times reshared it, BBC reshared it, and so on and so forth. You might have seen some titles like this: scientists discover powerful antibiotic using AI. Well, now you know. It was actually a human-AI synergy system where a graph machine learning model was trained to predict whether a molecule inhibits bacteria, and then we just sent the researchers from MIT who did this. They sent the top 100 molecules to chemists, and then they discovered this gold nugget in the middle of all of those molecules, right? Now, this is still to this day one of my favorite human-AI synergistic success stories in this space. The only unfortunate part which didn't give it the fame it deserved is, as you can see, all these articles were from February of 2020, so this was basically 1 month before the world went entirely crazy and just started talking about COVID and nothing else, and as a result, people suddenly didn't care about antibiotics that much. They cared a lot more about, viruses and antibodies and stuff like that, right? Okay. Now, so I hope this already motivates you that, like, even with a very simple question to a machine learning model, how confident are you in a particular decision, we might end up uncovering some pieces of science or some pieces of chemical space that we never thought to explore in this particular way. However, this work is just an example, and this work was not done by me. So I can only tell you from the outside how excited I am about it. So now I'm going to flip this over its head and tell you about something I have actually worked on, right? And the question I want you to keep in the back of your minds throughout this part of the talk is, can we discover new structures, so new results, new theory in pure mathematics using machine learning? Now, this is a very interesting question. We at DeepMind obviously believe that this could happen. And we talked to a few of our mathematician friends at the onset of this project about 2.5 years ago. And let's say mathematicians were not particularly excited about the concept. They were quite skeptical, right? They were like, yeah, but my field is too pure. There's not a lot of data. The data is not clean enough for you guys to make advantage of it. And also, your systems can only give like 80, 90% accuracy. In maths, it's all or nothing. You either get the theory right or it's wrong, right? So there were many reasons why people were skeptical about whether or not we can do anything in this space. Well, I'm standing here talking to you, so we clearly did something in this space. So let's see what we managed to do. First of all, why did we, resist all of those comments and keep working on it with some of our collaborators? Well, actually, when you think about it, and I hope there's some mathematicians in the audience, when you think about it, the act of doing mathematics is not just blindly following logical rules, and it's actually something that's a lot more creative and imaginatory, and I think this guy over here, Srinivasa Ramanujan, is the best example of this. For those who do not know him, Ramanujan was a completely self-taught mathematician, no formal training whatsoever, yet he came up with these amazing theorems and conjectures that felt like they materialized out of thin air. If you know the thing like, it just occurred to me in the shower, those kinds of ideas, right? So basically, you already on this very popular example, you can see maths is not just blindly applying abstract rules, but there's an aspect of creativity, there's an aspect of imagination in there. Another example, which is my personal favorite, is the work of this guy, Johannes Kepler. If you haven't heard about him, he invented the laws of planetary motion. So we know how all the planets in the solar system move because of this guy. How did he come up with these rules? He actually stared at years and years of astronomical data. So for every night, people would record where the planets were, and he observed, and he saw a pattern in how the planets were moving. And when he saw that pattern, he's famously quoted as saying that he first believed he was dreaming. Okay? So I'm just getting started telling you how research in mathematics looks like. And I've already mentioned creativity. I've already mentioned imagination. I've already mentioned dreams. And this, to be honest, is something that we believe we can positively influence. So this led us to believe, can we create an artificial intelligent power tool that can help the mathematician at times when they need some inspiration, some intuition, some creativity, something to just stimulate their way of thinking. We're not really imagining an AI system of today will be able to replace a mathematician precisely for the reasons that the mathematicians gave us. Like, these systems are not 100% accurate. They get it wrong, sometimes spectacularly, okay? However, they are really good at looking at patterns of things that humans just aren't that good at looking at, and therefore they might be able to help a mathematician see something when they have no idea even where to look. And that is what we tried to do here. So an AI-built power tool that's used in synergy by the mathematician, and you'll see it's a bit of a back and forth process with using the AI, which I find really fascinating, that led to, well, we believed that it would lead to something interesting, and in spite of all those comments we got initially, it did lead to something quite significant, because we have been able to, with the help of our mathematician collaborators from Oxford and the University of Sydney, we've been able to derive meaningful top-tier mathematical results in two very disparate areas of math that I'll tell you about in a second. And those results were by themselves strong enough to be published in a top-tier respective mathematical journal. And then the significance of those results was recognized by the top science journal in the world, Nature, where our work actually featured on the cover page. And you can see, I'll explain the significance of what's on the cover page in a few slides' time. But basically, this is more or less one of the top accolades in science that you can get. And it was followed by significant media coverage. Here I'm just mentioning the New Scientist article, but there's a lot more. Okay? But all of these things are a bit, consequential. Like, they happened after we did the work. What we found particularly meaningful was not the Nature cover itself, but what the mathematicians who reviewed our paper told us in their anonymous reviews. Remember, these people are anonymous, and it's kind of their job to criticize us as much as possible so that we have the best paper possible. Those mathematicians have written things like, this paper marks the beginning of a new phase in the use of computers in mathematical research, and I cannot imagine a mathematician not using these methods when available, because not using them means progressing much more slowly, okay? So this is a bit of a 180-degree turn back from, say, 2.5 years ago when we talked to mathematicians, and they were like, no, I don't really think you'll be able to do something in this space. Now they're like, this is actually a significant tool. I might want to use this in my day-to-day work. And also, we got Marcus du Sautoy from the University of Oxford, who gave us this really good quote which illustrates kind of what our system does. A bit like Galileo picking up a telescope and being able to gaze deep into the universe of data and see things never detected before. I'm not able to say poetic things like that, but hopefully I will make it a bit clearer what those telescopes have helped us see. Okay? So, now that I've kind of set the stage for the kind of circumstances that we worked on and the kinds of significance that our results did, let me tell you a little bit about our results. Now, of course, these are very intricate areas of math, and I'm not expecting many people in the audience, myself included, to truly understand what the mathematical results are about. That's down to the math reviewers who said this work is great, right? But what I want to impart on you in this talk is to tell you enough of the details so that you understand how the machine learning system was built and how the mathematician was able to interact with it to arrive at this conclusion. And I feel like that concept is something powerful that you can apply virtually anywhere, not necessarily only in maths. So the first area that we impacted is not theory. It's great because it allows me to draw these pretty animated diagrams. So we've all come across knots before, right? They're these twisted structures that cross themselves. Maybe the main difference between a mathematical knot and a knot that we see in real life is that this loop closes on itself. So it's like a three-dimensional shape that has some interesting crossings with itself, right? And mathematicians are really fascinated by these objects. Studying them has many implications across many areas, not only of math, but also physics and science and engineering, okay? And one thing that's quite fundamental is that when you have a knot structure like this, there are different ways of looking at that knot, right? So it's a structure that crosses itself. So you can imagine these crossings as sort of things you can do arithmetic with. And this gives you an algebraic view of the knot. Another option, as I just showed you, is to look at the knot as a three-dimensional object and study what the geometry or topology of that object is. Now, these are two fundamental ways of looking at knots, and there were many significant findings in these areas. But something quite significant was missing. Mathematicians didn't really have any idea if there was any connection between these two views. And our collaborators also, who were experts in the field, had no presumption on whether or not these two were connected, but they knew that it would be a very fundamental thing to try to establish whether or not there was such a connection, right? So what did we do, being the machine learning savvy people that we are? We built a data set of geometric quantities of knots, and we tried to train one of these neural networks to predict something algebraic about the knot, right? And specifically, we predicted this one quantity called the signature. It's not particularly important what it is. What's important is that it's an integer quantity, so we could do classification. As the machine learning people in the audience know, classification is a bit nicer to work with than regression. So you take just a bunch of these observed quantities about some knot, predict this algebraic quantity about that same knot, train a neural network like standard off-the-shelf MLP to predict this. And it turns out it was quite good, quite high accuracy, right? This obviously made the mathematicians quite excited, but it doesn't really lead to anywhere. Like as they say, you cannot publish a math paper saying, I trained a neural network and it achieved 97% accuracy. It doesn't work like that in math, right? You need to understand what's the science connecting this thing to this thing. And therefore, you need to interrogate this neural network. What has it actually learned to do? And there, this question that I mentioned to you earlier comes in handy. We can ask the network which patterns in the geometric quantities were most helpful that influence you to compute a particular signature. And what you get is an influence plot that looks something like this. So here you have all the geometric variables that we fed into our neural network. And this is the network's belief of how important they were in terms of gradients, okay? And hopefully it doesn't take a degree in advanced mathematics to tell that some variables are more important than others. So what did we do? We just communicated that to the mathematicians. Hey, you might want to look at these three guys, meridional and longitudinal translations. They seem to be quite important, right? They took these quantities, they went away for a few weeks, and then they came up with this fun, simple but nonlinear combination of these two quantities of a knot to derive something known as the natural slope, which was an obscure enough quantity that nobody ever computed it in a knot table before. But it turns out it's almost linearly related to what we want to compute on the other side. So that's almost there to having a pure mathematical discovery. The one thing that remains is to say, okay, so there's a linear relationship. 2 times the signature is roughly this slope. But you need to upper bound how much can you go wrong with this estimate. And at that point, you have a theory connecting the algebra and the geometry. So the mathematicians looked at this. They came up with the first conjecture using the knot's volume as the upper bound for this error. And it worked on all the knots in our data set, actually. However, the standard thing in machine learning, your model is as good as your data set. So if you try really hard, you can actually come up with these super twisted, braided knots that invalidate this conjecture altogether, right? So what did we do? Did we completely collapse at this point and cease all work and just concede defeat? No, not really. We just went back to this plot, right? Because there are some other variables in here. And while they're significantly less important than these guys, some of them are still more important than others. These 3 guys, for example, they seem a lot more important than everything else. So that's what we communicated to the mathematicians. Hey, this short geodesic, injectivity radius, cusp volume, they also seem to be somewhat important, not nearly as important as these guys, which means they probably are something that you can use to fix your error term, right? And the mathematicians took this, they went away for a few weeks, and using one of those guys, the injectivity radius, they were able to patch up their theory and actually came up with a formula they were able to prove. So this is now a proven mathematical fact, which, as far as we know, for the first time connects the algebra of a knot, the signature, with its geometry, using the slope, the volume, and the injectivity radius. So it was a very significant result in that regard. And just before you think that we got lucky, because obviously the neural network also suggested this guy a bit more than this guy, so you might say, okay, like the network was trying to fool us. Some months later, the mathematicians took this guy as well, and they were able to derive an equivalent theorem. So we really were not being fooled by the neural network here. It was telling us exactly what we need to look at. And now if you look at the cover of our Nature publication, now I can explain to you what it actually means. So here in the bottom, you have the machine learning world with like printed circuitry and processors and whatever. Here you have the mathematical world where the humans write down things on paper, and you have this one theorem that resulted as the synergy of the AI system in here and the human model in here. And everything kind of converges together to give us this equation that we've been able to prove a theorem around, right? So this was the first area of math that we've been able to influence. The second area that I was significantly more involved in, you'll see me as one of the co-authors on the paper actually, is representation theory. And I won't get into the details of representation theory. What I'll say is we're going to be looking at these objects called permutations. So a permutation, if you're not familiar, is a construct that takes a collection of objects and then just shuffles them around in some way, okay? So puts, say, A from the first place to the third place and so on and so forth. Okay? They're a very fundamental object in all of mathematics and recently also in machine learning. And one fundamental problem in representation theory, for 50 years it was basically not attacked whatsoever, but it's a super important problem, is the combinatorial invariance conjecture. What does it ask? You can put these permutations in a graph with each other, where the permutations are nodes in a graph, and the edges are swaps. So you take one swap to arrive from one permutation to another. And related to those graphs are these polynomials known as KL polynomials that are just polynomials with integer coefficients. And it's a very important foundational question in representation theory. Can we take this graph of permutations and compute the polynomial from it? Very fundamental question. But for 50 years, nobody really did anything significant on this problem. Now, you might be wondering, why is that? Well, in order to arrive at a rule to compute this polynomial, it needs to work for any power of that polynomial. So if there's a q squared or q cubed, it needs to be able to predict it correctly. So now let me show you, what do you think is the easiest graph for which a q squared appears? It is this graph over here, okay? So now you can see I had to make my graph substantially more complicated before even a tiny little insignificant q squared would appear. You can imagine how complicated this gets if you want to get to q cubed. So already at this point, you know, even if you're a top-tier mathematician, you cannot really see what's going on here, right? The human naked eye cannot really spot anything interesting happening here, right? And as our mathematician collaborator remarked, this is one of the easiest examples, so it only gets harder from here, right? So can a human ever really hope to manually arrive at a solution? This is where the AI system steps in and hopefully will act like a bit of a precision microscope to tell the mathematician you don't have to look at this whole structure. You can only look at, say, 10 nodes or something like that, which describes what you want to look at. So what did we do? This is where my expertise comes in, all that graph stuff I told you about before. Our input here is a graph. So I came in with my hammer, with my graph neural network, and I applied it to these graphs to predict the coefficients of the polynomials, right? Straightforward machine learning task. And it turned out that it wasn't quite good at first. It was about 60% accurate. So you ask it for the confidence, it was maybe about 65%. It was still better than chance, so we thought we were onto something. But obviously, as we said before in math, you cannot publish a paper saying you have a 65% accuracy on this thing. You need to understand what's the connection. So we tried to ask the second question. Which patterns in this graph influenced you to compute this polynomial? And because the input is a graph, in this case, these explanations will be like subgraphs, so some parts of the input graph, some nodes and edges that the model finds particularly important. Now, I must stress, initially, what came out of that question was not as nice looking as this. It was very noisy, very messy. I honestly thought we shouldn't even bother. We need to invent better techniques for extracting these things. But we sent it to the mathematician anyway. Maybe they find something. And after 2 weeks of staring at those very noisy graphs, our collaborator realized that these kinds of diamond structures appear quite a bit, and he saw them in some related work. So he was like, yeah, maybe these guys are important. So we thought, OK, let's retrain our graph neural network with the data about the diamonds given as extra features. So now you say, just an extra feature for every node, you say, is it in a diamond or not? So you tell to the model directly where the diamonds are. Our accuracy jumped from 65% to 98%. So this was, a very clear example of a back and forth between a mathematician and a machine learning model that led to a very huge jump in confidence that these diamonds were indeed very important. Now, of course, these diamonds are not the whole story. They are not sufficient to derive a mathematical theory. However, we could then ask this model again, what were the most important parts of the graph? And as I told you, the edges in this graph, the connections are swaps. So if we say have permutations of 9 elements, we can plot which swaps did the model prefer to do. So the items here are from 0 to 8, so 9 objects. And you have this heat map, simple exploratory data analysis saying which edges, which swaps did the model prefer to use when computing the polynomial. And you can see a very clear pattern. It really liked to swap item 0 and to swap item 8, what we call extremal reflections, so reflections of things at the extremes. Yeah? And this turned out to be a significant discovery, not only for the final theory, but also in the eyes of our anonymous reviewers. This is a quote from one of our Nature reviewers saying, "The feeling that these extremal reflections seem to be crucial is one they would have expected only from a handful of great world experts in representation theory, and it's such a human suggestion that," I quote, "it gave them goosebumps." Okay? So let's recap what we did here. We took a very rudimentary AI explainability technique, a very rudimentary data visualization technique, simple heat map, and that was enough to be goosebump inducing in a top mathematician. Can you imagine what they will start saying when we actually get good at this stuff? But using the diamonds and using these extremal reflections, our collaborator was able to figure out that there's a way to decompose a graph into these 2 parts, an inductive part and a hypercube part, such that you can then compute the polynomial from it. So we were able to prove a theorem that every graph like this can be decomposed into these 2 parts. You compute a polynomial from the 2 parts, you sum them together, and you get the thing that you want. Okay? And one thing that's also quite cool is that this polynomial that we're after is computed as a sum of this inductive part, which for human experts is very well understood. So this is easy to explain to a representation theorist. This part here came from these hypercube parts along the extremal reflections, and they were completely AI suggested. No human knew to look here before. So this is actually a quote from our math collaborator who worked with us on this. Like, the final formula being a sum of something that came from humans and something that came from AI is maybe the best possible embodiment of human-AI synergy you can get. The thing you want is literally a sum of something you know and something the AI tells you, right? Now, you might be wondering, because we proved this theorem, did we settle the 50-year-old grand challenge? We haven't, because it says there must exist a decomposition that works, but there could be many, many decompositions, and some of them might give you the wrong answer, right? So without a way to tell which decomposition is correct, you haven't solved the problem. So being the machine learning savvy people we are, we wanted to build a data set of a bunch of decompositions with a label saying, does it work, does it not work? And we did this for all permutation groups of up to 9 elements, which is 9 factorial many things. There's a lot of data in there. How many wrong examples did we find? 0, okay? Which from a machine learning standpoint is quite bad because we have a very imbalanced data set, right? But from a mathematician perspective, it also means that maybe no matter what decomposition you take, it will work. And we actually have this conjecture in our paper, and our mathematician was inspired enough by the structures we found that he even sketched a possible proof route. So if somebody who's savvy in perverse sheaves and these kinds of things wants to go take a whack at proving this conjecture, they have a blueprint that they can use to prove it. Okay? And this was all, as we said, came from a suggestion that came from the AI system. What I want to kind of leave you with, and hopefully this gives you a good overview of our work, is just a quick thought on what this means, on what could come next in human-AI synergy. Specifically, we have been able to take a standard off-the-shelf neural network model with very standard gradient saliency explainer methods, together with top-tier domain experts, leading to top-tier mathematical results that have already been published in top-tier mathematical journals, as well as Nature. So these kinds of things where you interact with the system and the system suggests you what to do to solve some engineering and scientific problem, I think is a very pervasive setting, not only in pure mathematics. Pure mathematics only takes it to the extreme where you cannot afford to be partially wrong, right? So if we were able to get this far in the purest of all fields with the simplest methods that came to our mind, I can only begin to imagine what might happen if you want to take this to the next level and get better at these methods at more interesting domains. And I'll just mention that we made all of our source code available on our GitHub profile of DeepMind. So if you want to look at the code we wrote and the simple techniques we used and the math data sets we played with, it's all out there, open, you can play with it. You don't even need a GPU to train these kinds of systems. They're that simple. So on that note, I will leave you with a thank you note. Thank you so much for inviting me. It's a great pleasure. It's my first time speaking in Croatia. I hope the first of many. I'd like to thank all of my great collaborators, both at DeepMind and at Mila, Oxford, and Sydney. And if you have any questions, I'd be delighted to take them. Thank you so much.